All right, one last topic, solvent, and this is a short topic. All chemistry is done in solvent. There are really two distinguishing factors of solvent. One is polarity. Solvents range, this is usually done on the basis of dielectric constant. Dielectric constant in vacuum is 1. Solvents generally go from very nonpolar things like cyclohexane, dielectric constant of a couple, 2, 3, I don't know, to rather polar things like DMSO. So that's one distinguishing factor. The second distinguishing factor is hydrogen bonding or not. The standard hydrogen bonding solvent, which is not very common in the organic world, is water. That also has a large dielectric constant. There are a lot of other hydrogen bonding solvents that are less effective than water, also less common. Methanol is a hydrogen bonding solvent. So there are two distinguishing things. It turns out that the polarity part is actually very easy to describe because there are no specific strong interactions. The hydrogen bonding part is very hard to describe. What I'm really saying is that solvation theory applied to anything but hydrogen bonding solvents is something that actually should be fairly straightforward to do. I'm not saying it's easy. Applied to hydrogen bonding solvents, particularly water, is a much harder problem. There are two general approaches to solvation. There's the approach that you would like to use but really can't, and that is what I'll call explicit. And what that is you take your molecule and you put it in a box of solvent, water, and you stir it up. What stirring it up means you sample over different conformations of the solute, different arrangements of the solvent. This is generally it's called molecular dynamics. The experience is that you need tens of thousands of structures in the average, and the only practical method is molecular mechanics. A lot of people do this. My own biased opinion is that it's a waste of time because the molecular mechanics, the ones that exist right now, are really rather poor describing inter and intramolecular interactions. And so I think as you average over 1 million, I'm not sure it's worth much. But that's my bias. You can't do this quantum mechanically. There are people that have begun to do this, called quantum molecular dynamics. They are based on extremely simple forms of density functional theory. I don't have any idea whether they're any good or not. Again, I'm a little bit biased to think that they're probably not very good. The practical approach, this isn't to say this, we're actually playing with this by trying to develop a better mechanics. The practical approach are what I'll call implicit models. There are lots of these. They fall into two categories. They fall into the models that I prefer, which are really very simple, and they're called continuum models. They're really simple, and then they fall into the kind that are empirical, that are also simple, but they have lots of parameters. We actually support both of those. I lean toward the continuum models simply because they appear to be better behaved. Again, they're a choice. Let me focus on one of them, which is called the CCPM model, which is about the simplest one of all. It's a model that can be applied not only to energies but also to derivatives, which means that you can, in principle, calculate structures in a solvent. They don't change very much, actually. You can calculate spectra in a solvent. There's very little experience with spectral calculations. It is possible to calculate not only infrared, but also, in principle, NMR, which is also a derivative. But there's very little experience with that. I'm not going to talk about that. So I'll just talk about energy. If you look at, I'll only look at pKa's. This is pKa's of carbon acids in DMSO. Okay, DMSO is a very high dielectric constant, but non-hydrogen bonding solvent. If you look at pKa versus gas, so this is doing calculation not in the solvent, and this is a least squares fit, so there's one parameter to bring the units the same, so I'm pKa. It's pretty bad, but at least there is clearly a relationship over, strong acids versus weak acids. If you now do this in the CCPM model, which is not very much more expensive, the correlation is clearly better. There's some outliers here which need to be questioned. There's an issue there. But you can see that in this simple case where we are getting, as we'd expect, an improvement. Now this I would expect the solvent model to actually work, because here we're non-hydrogen bonding. So I'd expect this to actually work. Here's a separate example. This is now in water. This is now a harder problem. What I'm looking at is strengths of very closely related compounds, amines, and there are a lot of these known, in the gas and in water. If I just take a simple example, ammonia to trimethylamine, in the gas there's this, which is what we calculate, there's a huge difference. This is 80 kilojoules more basic than ammonia. In solution, there's no difference. Ammonia and trimethylamine are the same, and the ones in the middle are actually more basic, so it's not linear all of a sudden. If you try to calculate this is the gas versus pKa. It's a scatter plot. I've drawn a line, but the line is garbage. This is a scatter plot. What this tells me is if I want to calculate aqueous phase basicity, this is also true with acidity, so this is the water case, the gas is not a good representative. Again, I'm doing a least squares fit just to get the units the same. If I do this in a solvent, this CCPM actually works much better than I would have predicted. It's certainly not perfect, but here's now applying this model, which I would not have guessed in the case of amines in water would be better. What it's telling me is the hydrogen bonds are not the primary reason that you're actually seeing an ordering here. It's telling me that we're actually not accounting for that. Okay, that's all I'm going to say.